Hi, welcome to cs517A. For this video lecture, I'm going to talk about file system implementation. File system provide efficient access to the disk by allowing data to be stored, located, and retrieved in a convenient way. A file system must be able to store the file, locate the file, and retrieve the file. Most of the operating systems use layering approach for every task, including file systems. Every layer of the file system is responsible for some activities. When an application program asks for a file, the first request is directed to the logical file system. The logical file system contains the metadata of the file and directory structure. If the application program doesn't have the required permissions of the file, then this layer will throw an error. Logical file systems also verify the path to the file. Generally, files are divided into various logical blocks. Files are to be stored in the hard disk and to be retrieved from the hard disk. Hard disk is divided into various tracks and sectors. Therefore, in order to store and retrieve the files, the logical blocks need to be mapped to physical blocks. This mapping is done by File Organization Module. It is also responsible for free space management. Once File Organization Module decided which physical block the application program needs, it passes this information to basic file system. The basic file system is responsible for issuing the commands to I/O control in order to fetch those blocks. I/O control contains the codes by using which it can access the hard disk. These codes are known as device drivers. I/O controls are also responsible for handling interrupts. Directory implementation. We can use several algorithms to implement directories. However, we should carefully consider what algorithm to use because it can significantly affect the system's performance. The directory implementation algorithms are classified according to the data structure they implement. There are mainly two algorithms which are used these days: linear list and hash table. Linear list. In this algorithm, all the files in a directory are maintained as singly lined list. Each file contains the pointers to the data blocks which are assigned to it and the next file in the directory. So this is how it looks. So you have the file name, and then after the file name you have another block there. It points to the data blocks, and then of course the next is the second file. So it's like a straight line. Hash table. To overcome the drawbacks of singly linked list implementation of directories, there is an alternative approach, that is hash table. This approach suggests to use hash table along with the linked list. Here, you still have the linked list here. See the problem with the linked list: when you add a new file, it's either added to the last part here or the first part, because it's one straight line. But with a hash table, you can already add in the middle and you can remove in the middle. So a key value pair for each file in the directory gets generated and stored in the hash table. The key can be determined by applying the hash function on the file name, while the key points to the corresponding file stored in the directory. Free space management. The memory space in a disk or in any other memory system is limited. Thus, there is a need to properly manage free spaces to allow users to optimize the available memory resources. The system maintains a list of free disk spaces. The free space list contains all the records of the free space disk block. When we create a file, we first search for the free space in the memory and then check in the free space list for the required amount of space that we need for our file. If the free space is available, then it is allocated to the new file. After that, the allocated space is deleted from the free space list. Whenever we delete a file, then its free memory space is added to the free space list. The following are the approaches used to maintain or manage the free disk spaces. First is bitmap or bit vector, linked list, grouping, counting. For bitmap, it's a series of or collection of bits where each bit corresponds to a disk block. The bit can take two values, obviously 1 and 0. 0 indicates that the block is allocated and 1 indicates a free block. For the linked list, in this approach, the free disk blocks are linked together. Free block contains a pointer to the next free block. The block number of the very first disk block is stored at a separate location on disk and is also cached in memory. Next, grouping. This approach stores the address of the free blocks in the first free block. The first free block stores the address of some, say, n free blocks. Out of these n blocks, the first n minus 1 blocks are actually free, and the last block contains the address of next free n blocks. Next, counting. This approach stores address of the first free disk block and a number n of free contiguous disk blocks that allow the first block that follow. Every entry in the list would contain address of first free disk block and a number n. Next, efficiency and performance. These tend to represent a major bottleneck in system performance since they are the slowest main computer component. The OS employs a variety of techniques to improve the efficiency and performance of the secondary storage. Efficiency and performance still. So efficiency depends on number 1, disk allocation, free space, and directory algorithms used by the OS. Number 2, types of data kept in files directory entry and the need to update the information in directory entry. On the other hand, performance depends on number 1, disk cache. This is the use of separate section of memory for frequently used blocks. Number 2, free behind. Removal of a page from the buffer as soon as the next page is requested. Number 3, read ahead. Requested page and several subsequent pages are read and cached. So even before these pages are needed, they're already put in the cache ready to be used. Number 4 is the use of virtual memory. Recovery. Consistent checking. The storing of certain data structure like directories and inodes. Inodes is equivalent for Linux. In memory, and the caching of this operation can speed up performance. But what happens if there is a system crash? All volatile memory structures are lost, and the information stored on the hard drive may be left in an inconsistent state. A consistency checker, fast check in Linux or check this or scan this in Windows, is often run at boot time or mount time, particularly if a system file was not closed down properly. That's why if you have a blackout or you did not close, you just Control Alt Delete, you did not properly shut down, you will always you will experience that your computer will run a scan this or check this. So basically, it's trying to recover some files that might have been corrupted. Some of the problems that consistency checker will look into. Number one, disk block allocated to files are also listed on the free list. And they're supposed to be allocated, so there should not be already in the free list. Number two, these blocks are neither allocated to files nor on the free list. So that's also a problem. A disk block is allocated to more than one file. Should only be one disk block to one file. The number of disk blocks allocated to a file is inconsistent with the file's stated size. Number 5. Properly allocated files which do not appear in any directory entry. Number 6. Two or more identical file names in the same directory. So, from the very beginning, you're not allowed to have same name, identical names in the directory. You can use another directory and have similar name, but in the same directory, you cannot do that. Most recovery tools and procedures are not directly managed by the OS. This may include, number 1, backup and storage plan, automatic backup procedures, backup storage system, and recovery software and others. Log Structured File System or LFS. Log Structured File System were introduced by Rosenblum and Austerhout in the early 90s to address the following issues: growing system memories, sequential I/O performance trumps over random I/O performance, inefficiency of existing file systems are not RAID aware. So growing system memories. With growing disk sizes, the amount of data that can be cached also increases. Since reads are serviced by the cache, the file system performance begins to depend solely on its write performance. Sequential I/O performance trumps over random I/O performance. Over the years, the bandwidth of accessing bits of the hard drive has increased because more bits can be accommodated over the same area. However, it is physically difficult for the small rotors to move the disk more quickly. Therefore, sequential access can improve disk performance significantly. Inefficiency of existing file system. Existing file system perform a large number of writes for as much as creating a new file, including inode, bitmap, and data block writes, and subsequent updates. The short 6 and rotational delays incurred reduces bandwidth. Last but not the least, file systems are not RAID aware. Further, file systems do not have any mechanism to counter the small write problems in RAID 4 and RAID 5. You will notice that all of this listed have something to do with hard disk and the rotating disk, the read-write arm. This is a little bit more outdated because I could picture some time from now most of us will be using SSD or solid state. So once we use solid state as our secondary memory, these problems are somehow limited. Medyo nabawasan na. To recap, various configurations and structures are implemented by the OS to provide efficient ways to manage users' files. These will include, but are not limited to, the management of directory, free spaces in the secondary memory, and file recovery. For further reading, you can click or copy paste these links. Thank you for listening.